In this video I'm going to explain how to create this simple simulation which gives us a graphical, intuitive understanding of differentiation. If you're interested in seeing how to create a simulation like this, then continue watching. So let's start off by opening up a browser and we can type in Desmos, that's D-E-S-M-O-S, and you'll see it comes up with a graphing calculator, so you can click on this link here and that's the graphing calculator set up for us. So what we're interested in is differentiating a function, so we're going to choose a function. We'll choose something simple to start with. We can call our function f of x, and that is equal to x squared, so it's going to be x, and to get the squared it's the little hat. On my keyboard that's just above the 6, so I can go shift number 6 and then I can put in the exponent, which is 2. So that's our function y equals x squared, and we want to differentiate that and we want to get a graphical intuitive understanding of what differentiation is. Now we're going to pick a point on the curve, and the point is going to move along the curve from one side to another. So we do that by putting in a point, which is 2 brackets. Now we can call our point some variable name. Now we're going to call it the variable name a. So we can go along a value of a, and then we can go up a value of f of a, and that will take us up onto the function. So we're going to have a point a, and we're going to go up to the y coordinate, which is the f of a. We click the slider and you can see the point has appeared, and this allows us to move along this point, move along the curve. Now what we want to do is differentiate this function, and we'll give the differentiated function a new name. So the new function is going to be g of x, and that's going to equal the differentiation of this function f of x. So to differentiate you do d and divide by, in this case it's going to be dx, and we can put the space in and we can put our function in, which is going to be our f of x. So this has given us the derived function, which is in purple. So let's check and see, and we'll get the intuition that we need in order to understand how this function here is in the straight line is related to this curve. Now let's say we pick a random point on this red curve. So let's say we go along to the point 1 and we go up till we hit the curve and we hit the curve at point 1 here. Now the gradient of that point, that is how steep that point is going to be given by the value of this straight line here. So for example, at this point here, the gradient at this point here is going to be the value of 2. And if you were to pick this point along here, 0.5, then the gradient at this point here is going to be a value of 1. Now if you come along this side here, if you go to a point -1, then the gradient at this point here is going to be a value of -2. So the height of this line here gives you the steepness or the gradient of the original function in red, and that's what the derivative does. Now what we want to do is draw the tangent line in to this point, but obviously we want to be able to draw the tangent line into every point given by this little dot here as it moves round the curve. So how are we going to do that? Now we know that the equation of a line is given by y equals mx plus c. Now the value of m is the gradient and the value of c is the point where it crosses the y-axis. Now if we leave out the value for c for the moment, then we can see that in order to find the gradient, well, the gradient is just going to be the value of our a. So in this case, if we put a, say, to a value of 1, so the value 1 is just how far along the x-axis you come until you get to the dot. So the gradient of that there is just going to be the derivative of this function at that point 1. So the derivative of the function is just given by our new function g of x. But it's going to be g of x at that point a, which is equal to 1. So the gradient is just going to be given by our g of a. Now the value of our x here, we wanting to find every single point on the line. So if we were to put in x minus a, then what we have done in effect is we'll have fixed the value of a as 1 here, and then the value of x is allowed to vary all the way along the line. So if a goes to 1 here, then what we can do is we can work out the gradient at this point. So we've got the gradient, and if we multiply it by some distance, so here's one of the values of the distance here, so we get gradient at that point times the distance will give us this height here. And then we'll change the value of x so that it becomes, say, the value of 3. So you would have 3 minus 1. So it would be the gradient at that point times the 3 minus 1, which is 2, which will give us the next point on the line up here. So we continue doing that for all of our values of x, and we're going to get this straight line here. Now it's not quite right because we want this straight line to actually be on top of the dot. But you can note here, if you look and see, the straight line is out, but it's only out by a factor of this height here, which is actually just the function of f at that point a. So if we just add on our plus f of a, then you'll see that we're going to get the final line which we're looking for, which is the tangent to this curve. So you can see it's going to follow this tangent line roundabout. Now what we want to do here is we don't want this derivative just to stay as it is. We want the derivative to appear as we move this tangent line roundabout the curve. So we can draw out our function here, g of x. So we've already actually got it here, we've got our g of x, but what we can do is we can change the values, so we use our curly brackets, and we can say that we want our value of our x to be less than the value of our a. And you can see here now what's going to happen is we move this down. You can see that the blue line, which is the derivative, starts to appear here. Now we could have done it the round other way about. We could have done it x is going to be greater than a, and then it would go from this side and it would run down. Now my personal preference is to make it as we showed originally. We'll make it less than, and it starts from the bottom left. So that ostensibly is everything that we wanted, but there's only one other thing that we're wanting to put in, and that is the actual value for the gradient, and we can work that out, and we'll do that right now. So let's create a new variable and we'll call it x1, and we're going to say that x1 is equal to the g of a. Now all the g of a is the gradient of the original function at a point a. So that's the gradient of this red function at this point where we see the dot. But you can see it's actually come up as undefined. And you see the reason for this is that we've defined this derivative here only as x is greater than a. So it really should be x is greater than or equal to. And that'll allow us to generate the gradient. So what we're saying here is that if we take, for example, this a is a value, let's put a to a value of 1. So a is a value of 1. We're saying that the gradient at this point 1 is a value of 2. And you can actually see that is because you go along 1 and you go up 2. So the gradient is 2. Now we want to go ahead and add another little point in which tells us a position where we're going to put the value for the gradient. So let's put the point in, and we'll put the point 2, 1. So that's this point here. Now we can go into the label, and now in the label we can actually write something in here. So we could write in gradient, and you can see it appearing here. And we can say the gradient is equal to, now we can pass a value in to this by using the dollar sign. So we put dollar and we open and close our curly brackets, and the value we want to put in is the gradient, and the gradient is just given by our x1. So we put our x1 in, and you can see the gradient appears here. Now we don't want this dot here, so we can take this dot away, and we can see it tells us the gradient is equal to 2. So that's us finished. Now you can see that if we move this value of a, you can see that the gradient changes. This is the gradient here. And also the tangent to the curve works its way round about the curve. And you can see the differentiated function appearing in purple here. Now all that remains is for us to spruce the whole thing up a bit. So what we can do is we can change this here and maybe make it dotted, and we can make it say green. And we can go in over here, and if we click in the reverse contrast, we can get into projector mode, and we can get rid of the grid. And you can see something that's similar to what I generated earlier. So if I was to press play on this and zoom out, then you can see that we've created exactly the simulation that I created at the beginning of the video. So of course, whenever you create the video, you could record only a certain section of it so that you miss out the rest of the Desmos graphics. Now there's one other thing we could do here with the simulation, and again this is to add in a folder, and we can call the folder differentiation, and we can place everything into the folder. So we can we'll put this in, and we'll put this in, and there's a couple of things we'll leave out, and you'll see why just in a moment. Okay, so yeah, that's going to be us. So whenever we close the folder, we're only going to be left with a function. So that's our f of x and the value of a. So it means that we can press play on that. And we can also change the function. So for example, we could change that to x cubed. And you can see that it generates the function, which is the derivative of x cubed, which is equal to 3x squared. And you can test out lots of different derivatives. So let's say, for example, we could put in ln x, that's the natural log of x, and it's actually going to be given by this curve here, which is 1 upon x. So this is a good way to check your understanding of differentiation. You can put in different functions here, so x to the power of 4, and you could work out your differentiation. So in this case here, the value of this is going to be 4x to the power of 3, and you can check that out by actually putting 4x to the power of 3 in, and you can see that you've got that correct because it sits exactly on top of the differentiated function here in purple. So this is a nice little tool to understand differentiation and also to check out your actual working. So you can put your different function in, we can differentiate it, you can check it on the tool and see whether you've actually got it correct or not. So that's all for this video. If you like more of this type of video, then leave a comment down below and I can produce more of these. I do quite enjoy them. I've done hundreds of them over the last couple of years, and the tool is really quite adaptive and it can do an awful lot more than what I show you here. So thank you for listening. I'll get you in the next video. Goodbye.